Welcome all. Now we are going to discuss Theorem 8.2. It has 4 statements. The first one is, let X be a normal space and Y be a closed subspace of X. Then X is a Banach space if and only if Y and the quotient space X by Y are Banach spaces in the induced norm and the quotient norm respectively. Okay. And the second one is, let x1, x2, etc. xm be normal spaces and x be their cross product. Then x1, x2, etc. xm are all Banach spaces if and only if x is a Banach space in one of the norms, norm P, given in Theorem 5.2c. And the third one is, let x and y be normal spaces and x not equal to set 0. Then BL of xy is a Banach space in the operator norm if and only if y is a Banach space. And the last one is, the dual x dash of every normal space x is a Banach space. Okay, now we will look at the proof. The first one we have to prove is, we have x and y where x is a normal space and y be a closed subspace of x. Then x is a Banach space if and only if y and x by y are Banach spaces. Okay, so for the first part we have x is a normal space and y is a closed subspace of capital X. Okay, suppose first that capital X is a normal space and which is a Banach space. Okay, that is, suppose capital X is a Banach space. We have to show that y is Banach and also the quotient space x by y is Banach. If capital X is a Banach space, we know that capital X is a complete normal space, and so we have given y is closed in X and so y is complete, because we know that every closed subspace of a complete space is complete, and so y is a complete space now, complete normal space, and so y is a Banach space in the induced norm. Okay, now we have to show that x by y is a Banach space in the quotient norm. We have given y is a closed subspace and so x by y is a quotient space. Now we have to show that it is Banach. Okay, for that consider a sequence xn plus y in x by y which is absolutely summable. Okay, so by Theorem 8.1 we can show that x by y is Banach if and only if every absolutely summable series is summable in x by y. Okay, for that we have chosen a sequence which is absolutely summable in x by y. Now we have to show that this sequence is summable in x by y. It is enough to show capital X by y is a Banach space. We have sequence xn plus y is absolutely summable means summation 1 to infinity triple norm of xn plus y is less than infinity. Let it be equation number 1. But we know that triple norm of xn plus y is equal to infimum of norm xn plus y where y element of y. Okay, so being the infimum, if we choose for every n equal to 1 to 3 1 by n square in the place of epsilon, and considering triple norm of xn plus y plus 1 by n square, which is clearly not a lower bound, so we can find an element yn, element of capital Y, such that norm xn plus yn is less than triple norm of xn plus y plus 1 by n square for every n equal to 1 to 3 etc. This is clearly possible by the properties of infimum. Okay, so taking summation, we can find summation 1 to infinity norm xn plus yn is less than summation 1 to infinity triple norm of xn plus y plus summation 1 to infinity 1 by n square. This means that summation 1 to infinity norm xn plus yn is less than infinity, because using equation 1, the summation in the right side, first summation in the right side is less than infinity, and summation 1 by n square is also less than infinity because it is a summable series because of the p series with p equal to 2. Okay, so we have summation n equal to 1 to infinity xn plus yn is an absolutely summable series in the Banach space capital X. Okay, So by theorem 8.1 we can say that that series also is summable, because in a Banach space every absolutely summable series is summable. And so we have summation 1 to infinity xn plus yn, which is absolutely summable now, is summable in capital X. Let the sum be small s. Okay, that is summation 1 to infinity xn plus yn is equal to s, which is clearly an element of capital X, because the series is summable in capital X. Okay, let it be equation number 2. Now for m equal to 1, 2, 3, etc., triple norm of summation 1 to m xn plus y minus s plus y is equal to triple norm of summation 1 to m xn minus s plus y. Okay, which is we know it is the infimum. Okay, so it is clearly less than every element of the set. So we are taking an element summation 1 to m yn, element of capital Y. This is clearly less than or equal to double norm of summation 1 to m xn minus s plus summation 1 to m yn. Okay, which is equal to summation norm of summation 1 to m xn plus yn minus s, which is clearly tends to 0 as m tends to infinity using equation number 2. We know that the summation 1 to infinity xn plus yn is equal to s. So letting m tends to infinity, we can say that the series n equal to 1 to m becomes n equal to 1 to infinity xn plus yn, which is equal to s. So the norm of this tends to 0 as m tends to infinity. Okay, so we have summation n equal to 1 to infinity xn plus y is equal to s plus y, which is an element of x by y clearly, because s is an element of capital X. Okay, letting m tends to infinity, we can say this clearly. And so now we have chosen a series which is absolutely summable in x by y. Now we have found that that series is summable in x by y. So by theorem 8.1 we can say that the quotient space x by y is a Banach space in the quotient norm. So we have proven the necessary part of this first statement, that is x is a Banach space implies y and x by y are Banach spaces. Now we have to prove the converse. For that, assume y and x by y are Banach spaces in the induced norm and the quotient norm respectively. Now we have to show that capital X is a Banach space. For that, consider a Cauchy sequence xn in capital X. Then we can write norm xn minus xm is less than epsilon by 2 for some for all n and m greater than or equal to some n naught. Okay. Now triple norm of xn plus capital Y minus xm plus capital Y, which is equal to triple norm of xn minus xm plus capital Y, which is clearly less than or equal to norm of xn minus xm, because triple norm is the infimum, so it is clearly less than each and every member of the set. And we know 0 is an element of capital Y, so norm xn minus xm is an element of the set considering the infimum. So this is clearly less than or equal to norm xn minus xm, which is less than epsilon by 2 for all n and m greater than or equal to n naught. This says that sequence xn plus y is a Cauchy sequence in the quotient space x by y, which is a Banach space by our supposition. So it converges. Let the converging point be x plus capital Y. Okay, that is the sequence xn plus y converges to x plus y in x by y. Then by theorem 5.2 we can say that there exists a sequence yn in capital Y such that xn plus yn converges to x in capital X. Okay, and so since it converges, sequence xn plus yn is a Cauchy sequence clearly in capital X. So we can write norm of xn plus yn minus xn plus ym is less than some epsilon by 2 for all n m greater than or equal to some k naught. Okay, by the definition of a Cauchy sequence. Then checking norm yn minus ym, we can see that by adding some terms, we can see that which is less than or equal to norm of xn plus yn minus xn plus ym plus norm of xn minus xm by the properties of norm also, which is less than epsilon by 2 plus epsilon by 2, which is equal to epsilon for every n and m greater than or equal to maximum of n naught and k naught. Okay, we have already seen that the terms, the two terms which is less than epsilon by 2 for every n and m greater than or equal to some n naught and some k naught. So in the maximum of n naught and k naught, we can see norm yn minus ym is less than epsilon. This means that sequence yn is a Cauchy sequence in capital Y, which is also a Banach space by our supposition. So it converges, let the point be small y, that is the sequence yn converges to small y in capital Y. Now then xn, which is equal to xn plus yn minus yn, converges to x minus y, which is an element of capital X clearly. Okay, because the sequence xn plus yn converges to small x and the sequence yn converges to small y, means this is sequence xn converges to x minus y in capital X. So we have chosen a Cauchy sequence in capital X and now it converges to some point in capital X. So every Cauchy sequence converges in capital X, means capital X is a Banach space. So if y and capital X by y are Banach spaces, then capital X is a Banach space. Now we have proven the first statement of the theorem. Okay. Now for the second part, assume x1, x2, etc. xm be Banach spaces and let capital X be the cross product x1 cross x2 cross etc. cross xm. We have to show that capital X is a Banach space in one of the norms, norm p, given by norm p of x is equal to norm 1 of x of 1 raised to p plus etc. plus norm m of x of m raised to p whole power 1 by p if 1 less than or equal to p less than infinity, and if p equal to infinity, norm p of x is equal to maximum of norm 1 of x of 1 etc. norm m of x of m. Okay, in any of the norms we have to show that capital X is a Banach space. For that, take a Cauchy sequence xn from capital X. Then we can write norm p of xn minus xm is less than epsilon for all n m greater than or equal to some n naught. Okay, this is what is norm p? If 1 less than or equal to p less than infinity, norm p is and if p equal to infinity, norm p is given in the formulas. So using that we can write this. Okay, and so considering the jth term, we can write norm j of xn of j minus xm of j is less than or equal to the total sum, that is norm p of xn minus xm, which is less than epsilon for every n and m greater than or equal to n naught. That is because xn is a Cauchy sequence. Okay, so this means that sequence xn of j is Cauchy in capital Xj. Okay, because of we are considered the jth term only, and so sequence xn of j is less than epsilon. Norm j of xn of j minus xm of j is less than epsilon for all n and m greater than or equal to n naught, means sequence xn of j is a Cauchy sequence in capital Xj, which is by our assumption a Banach space for every j equal to 1 to m. So it converges, let xn of j converges to x of j for every j equal to 1 to m, that is xn of 1 converges to x of 1 and xn of 2 converges to x of 2 etc. xn of m converges to x of m. Okay, so the sequence xn converges to x. What is x? What is the x is the ordered m tuple x of 1, x of 2 etc. x of m, which is clearly in the cross product, that is which is clearly a point in capital X. So we have chosen a Cauchy sequence xn from capital X and now it converges to a point in capital X. This means that capital X is a Banach space. Okay. Conversely, suppose the cross product capital X is a Banach space. We have to show each x1, x2, etc., xm are all Banach spaces. Okay. For that, fix some j in between 1 and m. Now, to show capital Xj is a Banach space, consider Cauchy sequence xn of j in xj, and using that, let xn be the ordered n tuple with the jth term equal to xn of j and all other terms are 0. Clearly is an element of x1 cross etc cross xm, that is, it is an element of capital X. Okay. Now, checking norm p of xn minus xm, we can see that which is equal to norm j of xn of j minus xm of j, which is clearly less than epsilon for all n m greater than or equal to n0 because sequence xn of j is Cauchy. This means that sequence xn is a Cauchy sequence in capital X, which is a Banach space by our assumption. So it converges. Let sequence xn converges to small x in capital X. Then sequence xn of j converges to x of j in capital Xj by theorem 5.2 C part. This means that sequence xn of j converges in capital Xj. So capital Xj is a Banach space for a fixed j between 1 and m. So this is true for every j between 1 and m. Thus we have found that x1, x2, etc. xm all are Banach spaces if the cross product capital X is Banach space. This is the proof of the second statement of the theorem. Now we have to prove the third one, which is very important. The third statement says if BL of xy is a Banach space, then y is a Banach space, and if y is a Banach space and x is a normal space, then BL of xy is Banach. Okay, so first we have x and y are normal spaces and x not equal to set 0. Suppose BL of xy is a Banach space, we have to show that y is a Banach space. Okay, so suppose BL of xy is a Banach space in the operator norm. Since capital X is not equal to set to 0, we can choose an element which is non-zero. Okay, choose a element of x with a not equal to 0. Then by theorem 7.10, we can see that there exists some f element of x dash with f of a equal to norm a, which is non-zero clearly, and norm f equal to 1. Okay, now consider a Cauchy sequence yn in capital Y. We have to show that capital Y is Banach. For that we are chosen a Cauchy sequence yn in capital Y, and using this Cauchy sequence define capital Fn as capital Fn of x is equal to small f of x into yn for every x element of capital X. Okay, then clearly Fn is a function from is a map from capital X to capital Y, because f is an element of x dash, so f from capital X to k, and yn is a sequence in capital Y, so clearly Fn from capital X to Y, and clearly Fn is linear also. The proof is given. Okay, it is clearly linear, and norm of Fn of x, which is equal to norm of what is Fn of x, that is small f of x into yn. Okay, and this is equal to modulus of f of x into norm yn, because f of x is an element of k, and so it comes outside, which is less than or equal to norm f into norm x into norm yn by the properties of norm. Okay, but we know norm f is equal to 1, so this is equal to norm yn into norm x. So for a fixed n, choose norm yn equal to alpha. We can see that norm Fn of x is less than or equal to alpha into norm x for a fixed n. This means that Fn is an element of BL of xy. This is true for every n equal to 1, 2, 3, etc. So we can see that Fn is an element of BL of xy for every n equal to 1, 2, 3, etc. Okay. Also, norm of Fn minus Fm is equal to supremum of all norm Fn minus Fm of x for x element of x with norm x less than or equal to 1. And by substituting Fn of x, Fm of x, and simplifying, we can see that this is equal to norm yn minus ym into norm f. Okay, and since norm f equal to 1, we can see that this is norm yn minus ym, which is less than epsilon for all n and m greater than or equal to n0, because we have chosen yn is a Cauchy sequence in capital Y. Okay, so this means that norm of fn minus fm is less than epsilon for every n and m greater than or equal to n naught. Means sequence fn is a Cauchy sequence in BL of xy, which is a Banach space by our supposition, and so it converges. Let sequence fn converges to some capital F in BL of xy. Okay, now for the non-zero element small a in capital X, fn of small a is equal to f of a into yn, and we know f of a is equal to norm a, and so this is equal to norm a into yn. This means that yn, which is equal to fn of a divided by norm a, which converges to capital F of a by norm a, element of, which is clearly an element of capital Y, because we have seen that fn converges to f, so fn of a converges to f of a. Okay, and f of a by norm a is clearly an element of y. So we have chosen a Cauchy sequence yn in capital Y, and now we have found that this Cauchy sequence converges to some point in capital Y. So every Cauchy sequence converges means capital Y is a Banach space. So if the BL of xy is a Banach space, then Y is a Banach space. Okay. For the converse, suppose capital Y is a Banach space, we have to show that BL of xy is Banach. For that, consider a Cauchy sequence fn in BL of xy. That means norm fn minus fm is less than epsilon for all n and m greater than or equal to some n naught. Then norm of fn of x minus fm of x, which is equal to norm of fn minus fm of x, which is less than or equal to norm of fn minus fm into norm x, and which is less than epsilon into norm x for every n and m greater than or equal to n naught, and for all x element of x. This means that for each fixed x element of x, the sequence fn of x is a Cauchy sequence in capital Y. And by our supposition, capital Y is a Banach space, so it converges. Let sequence fn of x converges to some capital F of x in capital Y. That is, capital F of x is limit n tends to infinity fn of x, which is clearly an element of y. That is f from x to y. And clearly f is linear also, since each fn is linear. Also, norm of fn of x minus fm of x. We have found that norm of fn of x minus fm of x is less than epsilon into norm x for every n and m greater than or equal to n naught, and for every x element of x. Okay, so letting m tends to infinity in this, we can see that norm of fn of x minus f of x is less than epsilon into norm x for every n greater than or equal to n naught, and for every x element of x. Let it be equation number 1. In particular, if we replace n equal to n naught, we can see that norm of fn naught of x minus f of x is less than epsilon into norm x for every x element of x. This means that fn naught minus f is an element of BL of xy. Okay, by theorem 6.2, this is an element of BL of xy. This says that fn naught minus f is clearly bounded. So it is a bounded linear map from x to y, and so fn naught minus f is an element of BL of xy. Then f is also an element of BL of xy, because f can be expressed as f is equal to fn naught minus f. Okay, and since BL of xy is a linear space, clearly f is an element of BL of xy. So we have seen that sequence fn converges to f, sequence fn of x converges to f of x, and f is an element of BL of xy. Also, we have to see one more thing, that is, from equation 1, taking supremum over all x element of x with norm x less than or equal to 1 on both sides, we can see that supremum of all norm fn minus x, supremum of all norm fn of x minus f of x over x element of x with norm x less than or equal to 1 is less than epsilon into supremum over supremum of all norm x over x element of x with norm x less than or equal to 1. This means that the left hand side is norm fn minus f is less than epsilon into 1. Okay, for every n greater than or equal to n naught. This is true. Means norm of fn minus f converges to 0 as n tends to infinity, since epsilon is arbitrary. This means that the Cauchy sequence we have chosen sequence Fn converges to capital F in BL of xy. Okay, so BL of xy is a Banach space because every Cauchy sequence converges in BL of xy, and so BL of xy is a Banach space, which is the proof of the third part. So if y is a Banach space, BL of xy is a Banach space, and if BL of xy is Banach, then y is Banach. Now we have to see the fourth statement, which is very simple. It is clearly the application of the third statement of this theorem. We have to prove that the dual x dash of every normed space x is a Banach space in this statement. For that, we have a normed space x, and we know the dual space capital X dash is nothing but equal to BL of x k, and we know that k is a Banach space. Okay, so by the C part above, we can clearly say that BL of xk is Banach. That means x dash is a Banach space. That means the dual x dash of every normed space is a Banach space. This is the proof. Thank you.